well?
Yes, we can do that. Right, you're all going to be muted now. Peter, do you want to set it up so that you can present?
You have to unmute me.
Yeah, you need to be unmuted, sorry.
Need to be unmuted.
There we are, that's it.
Yeah, I can't see where it says share. Do I use share?
At the bottom of the screen,
Yeah.
let me just show you. I'll show you on my, well, actually, I don't know whether I can. There's a bottom of the screen, there's a big green button that says share screen.
Yeah, I've got that one. Yeah.
Okay, if you click on there.
And then I click on my presentation.
You can click on your presentation or you can click on your whole screen. It's up to you.
And then I can.
That's it. You're coming up now. That's brilliant.
What I want to do is get rid of these buttons so I can actually get at the buttons I want to see. Slideshow. From beginning. Okay. That should be good, shouldn't it?
Brilliant.
Looks good to us.
Yeah, okay, I can start then. Okay, I'll go back to the... Okay, I'm going to begin now. I'm going to talk first of all about philosophy of realism. What does reality mean? And this is vital to the talk. There's two meanings in philosophy for reality, roughly speaking. One is that everything that we directly observe and is tangible to us, that's real. And the other is that it's an ultimate truth which determines everything, but somehow is hidden. We only see the appearances. Now, it seems to me that physics started trying to explain the first, but ended up explaining the second. And what we've been doing since Newton's time is been on a path towards increasing abstraction and away from the realism of the senses. And quantum mechanics pushes that to an extreme because we don't have an electron, there's no such thing, no coordinates in space and time, only probability amplitude. No such thing as the path of a particle, only the sum of all possible paths, etc. And as we probe, let me just move this out of the way if you don't mind. I want to move that somewhere else. Going to move that somewhere where I can't see it. Yep. Okay. So at the fundamental level, I'm sorry, I've gone past where I wanted to be. My screen isn't interactive. Yes. So even though experiments seem to give us tangible results, we talk about real particles hitting real detectors. We know it's not really like that. There's something else going on. And it could be that on some occasions, our tendency to describe physics in terms of this reality one, everything being tangible, deceives us. And perhaps we'd be better using a reality two a description instead. And I think a possible case is the conflation between quarks of theoretical physics and the partons of experiments. You do deep inelastic scattering experiments, knock things out of the proton or neutron, and you see partons. And we call them quarks, but they're not quite the same thing. They're clearly related, but they're not interchangeable with each other. So what's the problem that we're going to investigate? Well, the problem is that at the fundamental level, we got four forces in physics, and they act on the particles, quarks and leptons, which are really quantized fields, but we call them particles because they seem to be like particles. And these four forces have different characteristics, different sources. Gravity is a result of mass or mass energy, and it's attractive between identical particles and decreases with the square of the distance, in principle. The other three forces, we call them the gauge interactions, the electric, strong and weak, and these are mediated by exchange particles or bosons. We don't know whether gravity is. They're repulsive between identical particles, and each has a distinctive force law, and each has a gauge symmetry determined by a mathematical group, and each is different. Each does have a component which is inverse square, a Coulomb component as we call it, and this gives us what we call the magnitude or the forces coupling constant. Now, if you take the electric force, it's only the Coulomb component. There isn't anything else. It's just an inverse square law. And it's gauge symmetry, the mathematical group, which I mentioned, determining the interaction, its properties, and the bosons that are exchanged is called U1. And it's characterized by just one boson, which is the photon. If we take the other two forces, these have additional components. So the gauge symmetries and the boson exchanges are quite different from the electron. The strong interaction follows what we call an SU3 symmetry, and it takes place between quarks or antiquarks. There's no, other than quarks or antiquarks, the other types of particle leptons do not involve themselves in the strong interaction. And these come in three varieties, which are known as colors. They only exist in combinations, and all combinations have to be colorless. You either have three quark combinations, protons, neutrons, or a quark-antiquark, which we call mesons. And this SU3 symmetry, so an SUN is n squared minus 1 bosons. So SU3 is 3 squared minus 1 equals 8 exchange bosons. We call them gluons, and they're massless. The remaining force, the weak interaction, characteristic of all leptons as well as quarks, so all fundamental fermions, it has an SU2 symmetry. And what this force is a creator and destroyer. So fermions and antifermions annihilate to combine and to produce a boson, and a boson can split up to produce fermion and antifermion. And there's always this sort of dipolar aspect to it, which we'll mention later again. And this symmetry is SU2, so there are 2 squared minus 1 equals 3 exchange bosons. And these are called W plus, W minus, and Z0. And they're the only exchange bosons which have masses. All the others are massless. And in the case of W, the W's are electric charges as well. Now, the weak interaction is different from the others because it's spin dependent. Only left-handed fermions and right-handed antifermions interact weakly. At a deeper level, we can look at the sources of the 3 gauge interactions to be a kind of thing what we might call charge. Similar to electric charge, and electric charge is part of it. Electric charge is the well-known source of the electric force, but we've got justification for describing the sources of the other 2 interactions as strong and weak charges. And these charges are the generators of the 3 symmetries, U1, SU3, and SU2. Now, I think there's been a lot of confusion because we haven't sufficiently appreciated that these charges are totally independent interactions from each other. Even though we have what we call the electro-weak combination, it doesn't combine the charges. And this is reinforced by certain experimental results, baryon and lepton conservation, and ensure that strong and weak electric charges are distinct and they do not exchange themselves into each other. And I think theories which have tried to violate this principle have invariably come to grief, and I'll be mentioning at least one of them. And in my opinion, charge is one of the most important concepts in physics, and its true meaning is essential if we want to understand where physics comes from. And it's on the same level as space, time, and mass. And these 4 parameters form a group of order 4. This is something I found a long time ago in the 1970s, and I've been writing on it ever since, among other things. And part of the fundamental nature of this quartet, and they'll have 3 independent relationships, is reflected in the existence of fundamental constants, G, H bar, and C, the only 3 that are really fundamental. And we can combine these in dimensional analysis to yield what we call the Planck units, because Planck did this first. So we got Planck unit for each of space, time, mass, and charge. The charge is the least familiar, but it's going to be one of the most important in this talk. Now, Vanessa drew this diagram for me, and this diagram shows the relationships between the 4 fundamental parameters. And this symmetry is amazingly exact. I've never found anything that broke it, except what I'm going to talk about now. the parameters, these parameters are characterized by particular algebras. Time is complex numbers, which we also call pseudo-scalar. Space is vector. Mass is real, and charge is quaternion. The three of them, and they're imaginary. If we combine these, we will get a group of 64 units. And this group requires just 5 generators. It turns out that that group is the group of the Dirac algebra, of the Dirac equation. So it's a very important group. But we only need 5 generators. In other words, if we had 5 terms, we could get the whole group without having to use all the others. And one way of creating those generators is to take the charge units onto each of the other 3. So those red charge units go onto time, space, and mass units. And we get the following combined units. And these are the generators of the group, one set of generators of the group. And the price of creating the generators in that way is that you're breaking the symmetry of the charges. You can see each of the charges, the K, I, and J, are tied up to different types of algebraic units. So each ends up with a different property. So this broken symmetry of charge is fundamental to the whole concept of interactions in physics. And if you follow it through to its logical conclusion, you will realize why you get the SU2 group for the first one, IK, why you get the SU3 group for the next 3 with together, the I, JI, and KI, and the U1 for the final one. So that creation of those symmetries comes from this breaking of symmetry of charge in creating this algebra. It also, at the same time, creates new compound and quantized local physical quantities. Before this, we only had space, time, mass, and charge. Now we have energy, momentum, and rest mass. Rest mass is not the same as mass energy, which is what we were talking about earlier when we talked about mass. If we put those together, that object in a bracket squares to 0 because it produces Einstein's relativity energy equation, E squared minus B squared minus M squared equals 0. And in a quantized form, if we quantize, say, the first bracket in the standard quantization procedure, we will get a version of the Dirac equation, which we can call the nilpotent Dirac equation. And we generate a whole form of quantum mechanics called nilpotent quantum mechanics. So each of those brackets is a square root of 0, which is why we call it a nilpotent. Now, if we put the forces and the particles together, we get what we call the standard model of physics. We have 3 generations of particles, more or less duplicates of each other. And the first generation has an up quark in 3 colors with electric charge 2e/3. A down quark in 3 colors with electric charge minus e/3, an electron with electric charge minus e. And there's also an electron neutrino with no electric charge. If we put all the charges together for both left and right-handed particles, which is okay for the electric interaction, not for the weak, but for the electric, it's okay. Interestingly, and square them, we will get 16/3. And this is an important number which we'll use later. Those are the standard model particles. Each column there is 1 generation. So it's duplicated in the second and third generation, the first is. And the fourth column is the gauge bosons for the 3 interactions that have gauge bosons. But there are 2 quarks and 2 leptons in each generation. Now, this is a fantastic theory. It's the most successful ever devised, completed about 1973, and hardly anything has happened which has changed it in any significant way. So all we have to do is, well, it's very difficult, but it's still possible. We calculate the results of an experiment that we can predict it. We have an equation, we solve it iteratively to take to whatever order of magnitude we want. And we know how all the fields work, and we know how all the particles, what they are. We know how everything happens. We just don't know why. Why do we have 4 interactions? Why do we have gravity and then 3 gauge interactions? Why do they have different force laws, gauge symmetries? Why they're different? How do they connect? These are the things we don't know. However, two things in the 1960s and 1970s seem to give us some kind of idea of how to go forward. The first was the Glashow-Weinberg-Salam theory combining, inverted commas, the weak and electric interactions. That was 1967. And the second was the possibility of a grand unification of the three gauge forces at a high enough energy regime. And that was due to Georgian Glashow in 1974. So let's start with the electroweak theory. This is a bit technical, so I'll skip over it fairly quickly. The electric and weak interactions are combined mathematically into an SU2 cross U1 gauge group, a combined group. And so this combines the original isospin fields and the weak hypercharge field. We started off with 4 fields in this, 3 W's and B. And we combine the last 2, the W3 and the B, into 2 new fields. And one of those becomes the photon, because originally the 4 fields were massive, but we need a massless photon for the electric interaction. So we have a mixing between W3 and B, creating new fields, Z0 and gamma. There is a parameter which quantifies the mixing, and we call it the weak mixing angle, theta W. And the sine squared of this fixes the ratio of the charge squared for the weak and the charge squared for the electric interactions. And the cosine defines the mass ratio of the W and Z bosons. So it's a very important parameter. Now, current measurements can measure that parameter, and it says that at the energy of the W and Z masses, what we call the weak scale, then also electroweak scale even, sine squared theta W is 0.231 plus or minus something. Now, it's significant that the value is not 1. Because it's not 1, it means that we've got to be careful if we say the electric and weak forces have become a single force. Some authors say that, but they're not correct, because these are still distinct. If they were 1, they might be the same, but they are not 1. We've shown that they're connected, but they have different sources and don't have the same coupling constant. So connected doesn't mean interchangeable, and the sources are not interchangeable. Neutrinos don't suddenly become electrons. They don't suddenly acquire electric charges. The second development, a potential development, because it's never been totally realized, grand unification. Now, this is possible because though charges are conserved as units, so when we say there are 5 electric charges, there will remain 5 electric charges, but their actual value in terms of energy interaction changes with the strength of the field they're involved with. And this is because particles like electrons polarize the vacuum around them and produce more electron-positron pairs, virtual ones, which produce further ones, and so to infinity. And you think, well, that's going to be impossible. But fortunately, it isn't. Even though all the gauge forces act in this way, the potentially infinite series of interactions can be shown to yield a finite sum. And we use a process called renormalization to do it. And this, by the way, is why quantum gravity doesn't work at the moment, because we can't renormalize it. But we can renormalize all of the other 3 interactions. The weak can only be renormalized when it's combined with the electric. Now, the parameter that we use is called the fine structure constant for each interaction. And this is the ratio of the charge squared to the charge of the Planck charge, the square of the Planck charge. So the electric fine structure constant would be E squared over H bar C. I'm ignoring the 4 pi epsilon null, which comes out just from using SI units. So each charge has its own fine structure constant. And given any energy, mu has a value determined by renormalization. And there are standard formula which have been long worked out for these. And they determine on the gauge symmetry which each force has. So they're slightly different for each one. So if you take the SU2 weak and the SU2 strong, the first order equations, you can actually do it more refined and do further orders. But the first order equations, which is what most people look at, are as given there. And the only difference between them is 5 over 6 pi for the weak and 7 over 4 pi for the strong. The logarithmic term shows that there's a huge input from the field. You don't necessarily have to write the equations in this way. The final mass doesn't have to be grand unification mass mx, and the final fine structure constant doesn't have to be the grand unification fine structure constant. It could be any, but I'm writing it in terms of the GU ones. And these two constants, so-called, they're not actually constants at all. They decrease with increasing energy. Now, the remaining one for the electric interaction, which is given by the following formula, you see that's got a difference, got a plus for the logarithmic term instead of minus. So this one increases. So if one increases and the other two decrease, maybe they converge. And this idea was put forward by George and Glashow. Now, you've got a slight problem that you can't measure the weak coupling directly in the same way as you can measure the strong and electric, but you can determine it through calculations of sine squared theta w. On the assumption that the interactions can be accommodated into an even bigger group. The three groups can be incorporated in a bigger group. And the smallest, simplest group, which accommodates all three of SU3, SU2, and 8U1 is SU5. And that's what George and Glashow put forward. And this followed on from the SU2 cross U1 unification of the electric and weak. So George and Glashow showed that in any grand unification scheme determined by a single gauge group, you could work out sine squared theta w exactly. And it's given by the ratio of the sum of all the squared units of weak isospin, which stands in for weak charge, and they're all half anyway, plus or minus a half. So the squared units are a quarter. For all the fermions in the standard model to the sum of their squared units of electric charge. So it's fairly easy doing the isospin units because we've got 8 if we count only the left-handed contributions, remembering that it only works if it's left-handed. So adding up all the different units, each a quarter, there's 8 of them, so we get a total of 2. Now, if we take the Quark model as proposed by Gelman and Zweig in 1964, with both left and right-handed contributions to electric charges, we get the sum that we obtained earlier, 16 over 3. And if we just put that into the sine squared theta w, we'll get 0.375. So that would be the calculated value for this case. Now, these are the graphs for the fine structure constants of the different interactions. And we can see that they sort of come near together, but they don't quite. There's a big difference between meeting in a triangle and meeting in a point, and these meeting in a triangle, because any 3 lines will meet in a triangle. It's not a huge triangle, but it's big enough to cause a problem. And this value turned out to be about 10 to the 15 GeV, the energy at which this happened. And so this theory raised a lot of hopes. And I remember reading about it almost as soon as it came off the press. Because it's a near convergence at 10 to the 15 GeV. And this is a very interesting number because it's only a few orders of magnitude below the magical Planck mass. The key value for quantum gravity at 1.2 times 10 to the 19 GeV. Maybe we can have a 4-force unification. However, I have to say that many decades later, these hopes have not been met. First, the hope for convergence didn't materialize. Secondly, the SU5 predicted a new range of X and Y bosons. And these X and Y bosons, unlike others, carried all 3 gauge interactions at once. And they seemed to require a decay of the proton. And there was a big effort made to find that, and that has not happened either. Nobody has discovered that. Claims were made early on, but they soon turned out to be wrong. And then there's a bigger, even bigger problem, in my view, with sine squared theta w. It's calculated from the theory at 0.375, and it's nothing like the experimental value of 0.231. And that would immediately raise the red flag for me. It's the one thing that you can calculate absolutely gives totally the wrong answer. Now, there was a claim that the parameter would be renormalized at higher energies to about 0.2, but we'll have something to say about that later. There was an attempt to save the situation by invoking supersymmetry by Amaldi et al. In 1991. So you find exactly the right kind of supersymmetry, exactly the right particles, exactly the right energy, then the values of the alpha terms will be reduced, leading to an exact unification at 10 to the 16. Now, this has been claimed, and still is, that this is evidence for supersymmetry. I think anybody who really believes in the standard model cannot believe that sort of claim. Anybody who believes in the scientific method would not accept that. You cannot say that such guesswork is evidence. The chance of a random guess being true like that is almost negligible. In any case, no such evidence has been found for supersymmetry, and it looks like we have to abandon that as well. And a very influential and decisive commentator on many aspects of modern physics, Ethan Siegel, suggests that the granification may be a dead end for physics. And this is the supposed granification using supersymmetry. So, should we abandon all hope of granification? Well, I first started investigating this subject in the 1990s, partly with my colleague John Cullen. And I put down the equations for renormalization. I took them out of the textbooks and worked with them. And I tried putting in 10 to the 15 and 10 to the 16 for the grand unification mass. As soon as I did that, I got nonsense for the individual equations. They simply wouldn't work. Nor did sine squared theta renormalize in the way they claimed. Instead of decreasing with energy, it increased, and it became 0.6 at grand unification, not 0.2. So this, to me, looks like the convergence is merely a result of compensating errors, and it's not actually fundamental at all. But even more significant than this is the fact that the graphs don't represent the convergence of the gauge interactions at all. For if I go back to them for one moment, you see that doesn't say alpha on the top graph, it says alpha 1. And alpha 1 is not alpha. Alpha 1 is not the fine structure constant for the electric interaction, but some sort of electro-weak hybrid. So instead of using the one for the electric interaction, the first equation, they have a hybrid, which is made up of the electric and the weak. Now, I can't see any sense in unifying electro-weak, weak and strong. That's not the same as electric weak and strong. But I can see why they did it, because if we use the alpha equation instead of alpha 1, there wouldn't be anything remotely resembling convergence. It would be completely off convergence. But as I say, I also came into the problem with a more flexible attitude to the nature of quarks than has been usual since, say, 1980. And this may lead us to a remarkable solution of the problem if we follow it. Here I need the concepts of realism with which I started. Now, I haven't the slightest doubt that all experimental quantum electrodynamic studies using deep inelastic scattering shows that up quark behave as though they have 2/3 of the value of the fundamental unit charge, of the electron charge. Down quarks behave as though they've got -1. True at all energies, there's no evidence of any transition at higher energies. The quark Compton numbers would be as follows, like that. The 2e/3 for the up, minus e/3 for the down, and b/3 for the baryon number, which is effectively what we might call the strong charge. It would be split between the three of them. And notice these quarks look identical. The colors show no differences whatsoever. Color has to be an added property superposed. An experiment shows that they correctly use fractional charges. You can do any experiment you want and you will always get those charges for quarks. But we don't know in principle if these are fundamental or if they stem from a broken symmetry. Are we talking about reality 1 or reality 2 here? And we have to separate the two ideas. Experimental measurements of fractional charges may be a result of competing symmetries, and I'm going to show how this could be possible. And there are serious problems with the idea anyway. Do we have to redefine the fundamental unit charge as E over 3 instead of E? Does this mean the electron is not a fundamental particle? Does that mean that we can shove together 3 mutually repelling electric 1 over 3 charges in a point-like structure? And can we do the same with an up quark with 2? However, the original and now standard Gelman-Zweig version was not the only quark model proposed. Now, Greenberg, who was one of the major players because he first came up with the quantum number color, wrote in 2015. In 1965, Han and Nambu later won a Nobel Prize, introduced, not for this though, introduced a model in which an SU3 color group is explicit. They avoided fractional electric charges by introducing 9 quarks with integer charges. He continued, but they paid the price that color was not an exact symmetry. Moreover, the notion of integer quarks ended up conflicting with later experimental evidence. I'm going to say both of those claims are wrong. The Han-Nambu model was the first to introduce color as a gauge symmetry, and the paper is endlessly quoted in that connection, but the other aspect of it is not quoted. But this idea that this is the first color as a gauge symmetry. This is their model. +1, +1, -1, and 1 baryon number on 1 quark at one time. Now, I was particularly interested in the fact that there's 1 baryon number. Now, Han and Nambu might have thought that color singlets or separated quark would emerge at higher energies. And this is what Greenberg was talking about. But it seems that the color symmetry is never broken. The symmetry is exact because the strong interaction is perfectly gauge invariant as massless bosons. It's completely gauge invariant, so it never breaks up. And I think that means that Greenberg's claim that the color was not an exact symmetry in their model is utterly incorrect, because their model doesn't say anything about higher energies, it just says it's an exact symmetry. So if the symmetry is exact, then there's no problem with color. It's entirely due to the strong force or color charge and has nothing to do with any other charges that are present, electric or weak. There's no problem with experiment because quantum electrodynamics and quantum chromodynamics, the theory of the strong interaction, are totally independent. I don't think QED phenomenology can decide the question of which basic structure of charges to use in other areas, such as grand unification or the gauge relations between the interactions. So I don't think it can even determine sine squared theta W, because that's two separate interactions. And our fundamental phenomenology and our fundamental methodology suggests that we go for the best fit with the symmetry. And if that leads to modifications in our usual practice, so be it. And let's see what consequences would come. Reality 2 in preference to reality 1. And in fact, there is one of exceptional interest, as we'll see. Frank Close, who I've met quite a few times and know quite well, he wrote in a textbook in 1979, imagine what would happen if the color non-singlets were pushed to infinite masses. Clearly only color 1 singlets would exist as physically observable states, and quarks would be in consequence be permanently confined. At any finite energy, we'd only see the average quark changes in phenomenology. Logically, we could not distinguish this from the Gelman model where the quarks form 3 identical triplets. Now, unfortunately, this is largely ignored, but it's never ceased to be correct. What he said then is as true now. The claim that experimental evidence is against the model is totally false, because the experimental evidence doesn't concern the model. It only concerns QED of partons as we measure them. It doesn't concern anything to do with the strong interaction. And in fact, I will show that experimental evidence is in favor of the model instead of against it. Now, interestingly, within a few years of Close's statement, there was a remarkable discovery made by Lachlan of the fractional quantum Hall effect. Electrons assumed effective charges of E/3 and E/5, even though they still remained as full electrons, and many other fractional values by forming pseudo-bosonic combinations with odd numbers of magnetic flux lines, and they were shared out between them. So as long as the total number of fermions, that's electrons and flux lines, is even, then the collective boson states can form. 3 electrons can combine with 5 flux lines to produce effective charge in each flux line of 3 E/5. Now, this was made soon after that statement by Close, but it doesn't seem to have made any difference to our understanding of the quark model, even though the discoverer in his Nobel lecture said it should. He said the fractional quantum Hall effect is fascinating for a long list of reasons, but it is important, in my view, primarily for one. It establishes experimentally that both particles carrying an exact fraction of electric charge and powerful gauge forces between these particles, two central postulates of the standard model that elements can arise spontaneously as emergent phenomena. So we could have the fractional charges as emergent phenomena, even in particle physics. Other important aspects of the standard model, such as free fermions, relativity, etc., already have at solid state analogues, and in some cases we even model after them. But fractional quantum numbers and gauge fields were thought to be fundamental, meaning that one had to postulate, and this is evidently not true. Now, I want to compare the Han-Nambu quarks and the fractional quantum Hall electrons, because in each case, the QED phenomenology is defined by a totally external agent. It's not defined by the QED. In the first case, a totally gauge-invariant strong interaction acts independently of any electric charges. This makes the composite baryon, neutron or proton, by combining quarks into a collective structure, which then determines its QED. In the second case, a gauge-invariant weak interaction, fermion or boson converter, acts independently of any electric charges. So the collective states of electrons in flux lines are governed by this weak interaction, then determine its QED. So you've got external agents in both cases, the other two forces. Now, at a very early stage in the 1970s, I thought Han-Nambu quarks could give a model for the strong interaction by rotating the strong charges between 3 possible allocations. And I'll show you the diagrams in a moment. And this model was able to generate plausible explanations of masses of the composite particles, the baryons and mesons. 2 things made it more plausible subsequently. These were the nilpotent form of quantum mechanics, which is my own development, and the proton spin crisis, which emerged from the EMC experiment of 1987, which some of my colleagues were involved in, as well as John is attending this lecture, John Williamson. So if we look at the tables of quarks and leptons, we will see, what I'm really interested in here is, if you look at the A table here, and look at the second line, plus S, this is the strong charge allocation, and there's 1 in the blue, and there's nothing in the others. If you go over to B, you see the 1 is now in the red, and if you go over to the C, you see the 1 is now in the green. I'll leave the lepton table out. So that was that. So that was interesting to me, and I was interested how you could do that, and I was able to get a lot of the properties of the composite particles from those tables. But later on, I had a version of quantum mechanical nilpotent structure for the baryons, separating out 3 components of momentum. So I said, what makes the 3 components of the wave function of this object? So it can't be 3 identical nilpotents, because that would 0, but it could be 3 with different values of momentum, X, Y, and Z directions. And spin defined in only one direction at a time. So the wave function reduces, in fact, to just that one with the single momentum in. And I found 6 separate phases, 3 phases and 3 antiphases, if you like. And you imagine that these happen all at once, but it's as though they were rotating between them at some regular rate. And I was able to apply that to the gluons, which I'll leave that. But the 6 phases must be all valid at the same time. This is gauge invariance, rotation symmetry. The symmetry is recognizably that of the group SU3. It's exactly the same as SU3 symmetry. The same structure as the 3 symmetric and 3 antisymmetric color combinations of the standard representation. And again, it suggests that the baryon number is rotated between the quarks as in hand number, not divided between them. And then we look at the EMC experiment, said that the total spin of a baryon, like a proton or a neutron, does not come from the addition of the spins of the 3 component quarks, the 3 valence quarks. And I thought this was more suggestive, with only 1 quark active at a time, if you like, in contributing to the angular momentum operator. And it seems to be about 1/3 of the baryon spin is due to the valence quarks. Later experiments have refined it to be that. And then the rest of the spin is due to vacuum contribution, but we don't need to discuss that. Now, if we use this model of quarks, how would it affect the quantities observed in gauge interactions? It wouldn't make any difference to the weak at all. We would still get the same summation for the weak components. It'd still be 2. But for the electric, with left and right-handed components, it would look totally different. We'd have lots of 1s and 0s as the squared charges 1 or plus or minus 1 or 0. And it would total 8. And sine squared theta W would now be 0.25. Now, Weinberg said that 0.375 is in gross disagreement with the experimental value at the mass of the Z particle. And this is a sure sign there's something intrinsically wrong with the calculation. But 0.25 is much closer. And it may well be really 0.25, because when we measure it, and I've looked at second order on this, and I've examined publications on this, and it seems that the production of W and Z actually produces a dip in the measured value. So we're actually measuring it through the production of W and Z. And so that's why we don't get the value that exactly that we would calculate, but it's pretty close. And it's interesting also that 0.25, if we got rid of all quarks and only had leptons, that would be what we would find for leptons. And why should an electroweak parameter, which has nothing to do with a strong interaction, be different in the quark and lepton sectors? I don't think it should. The Han-Nambo model, unlike the Gell-Mann-Zweig one, makes quarks lepton-like, allowing a real unification of these sectors, such as people always wanted to do. Now, there are some significant consequences of calculating an independent and credible value of sine squared theta W at the electroweak scale. We can now produce a much simpler calculation for the grand unification mass. We don't need to make any assumptions about the group structure. We can avoid the awkward one, the electric one, to begin with. We will bring it in later. We can do it just using 1/alpha2 and 1/alpha3, strong, weak and strong. But the other thing is that the hypercharge numbers, the U1 numbers for the electromagnetic running coupling equation, will not be the same as if we'd based it on pure QED phenomenology. Now, if you go back to the original graphs, what we see there, if you look at alpha2 and alpha3, we see that those are pushing the value much higher than alpha1, perhaps towards 10 to the 17. And if we change the sine squared theta W value, they might be pushed higher. They may even get to 10 to the 19. So let's have a look. So that's what I'm saying there. So if we take those 2 key equations, the alpha2 and alpha3, all we need to do is now is get in exact values of the measured values of mu and alpha, and just substitute them in and solve them as simultaneous equations. So we got good values for alpha 3 at mz squared, 0.118, and we got good values for alpha, 1 over 128. And these are at the value mz equals 91.2 GeV. We got a calculated value of 0.25 for sine squared theta, and we believe that's the real value. That allows us to convert the alpha measure into alpha 2. And now if we solve the two equations, we obtain an extraordinary result. We get a value of the grand unified energy scale of 2.8 times 10 to the 19 GeV. Now I know that the Planck mass is 1.22 times, but you've got to remember that these are approximate equations. There's logarithmic terms and there's all kinds of things. And in this case, I've gone into second order again and found out the first order, I haven't found it out, but found that other people have found out first order calculations massively overestimate the value of grand unification mass by more than 50%, maybe more than 60. So that would reduce the value into something in the 1 point something region, not far from 1.22. Now, if we assume that mx is the Planck mass, then we can find alpha g, the grand unification value for all interactions, 1 over 52.4, and we get a good value for alpha 2. Can we include the electric force? Well, the original GU used c squared is sine squared theta, and we have 5 over 3 involved. And let's look at the fermionic contribution to QED vacuum polarization for fundamental fractional charges. Do all that summation and you get 5 over 3 pi. Do it for integer charges and you get 3 over pi. And that 3 and that 5 over 3 become involved in the sine squared theta W value. So let's say that instead of having 5 over 3 pi in the equation, we have 3 over pi for our alpha equation. And we don't need to use that alpha to work out what sine squared theta W is. We can put the equations together and get a value like that. So we can now make direct use of the value for 1 over alpha, the alpha equation. And let's assume we've got grand unification at the Planck mass. And let's work out what the alpha will be. And we get 1 over 128 at mz, which is exactly the value we started with, but using a totally different equation from a totally different source. Conversely, we could do it the other way. We could start with 1 over 128 and we get mx is 1.42, which is an even better approximation to the grand unification mass. I say this is striking confirmation of the assumptions made from the first calculation because coincidental agreements are most unlikely for equation involving logarithmic terms. And it's particularly significant because it says that grand unification at this value might involve a direct numerical equalization of the strengths of 3 or even 4 physical forces. So we now have our set of equations from which all this can be calculated. And we got one for sine squared theta W as well. And if you look at the sine squared theta W equation and do a quick calculation, if you make mx and mu the same, so we take the energy of the grand unification, then the logarithmic term will disappear. And of course, if there's grand unification, then alpha will equal alpha 3. So we will get sine squared theta W equals 1. And this is the only way you can truly unify electric and weak if there isn't some sort of peculiar numerical division between them, if they look exactly the same. And this is the graphs that I've drawn for those 3 coupling constants. And we get, see, it's 19, 10, there's 10 to the power down below. That's 10 to the 19. And that's the sine squared theta W. It doesn't go to 0.2, it goes to 1. So what happens at grand unification? We can suppose that all 4 forces are reduced to scalar phases. All the other parts of the force disappear. They've only got U1 symmetry and purely Coulombic interaction. All distinguishing aspects of the weak-strong interactions having diminished to zero. And we get completely testable predictions, ones that ought to be testable now, because we know what alpha G and MX are. And so we can say what would happen at 14 TeV, which is the highest energy machine we have at the moment. Alpha would be 1 over 118. And if you take the minimal SU5 theory of George and Glashow, that would be 1 over 125. That's very definitely different. And we could do that if we could do QED at that energy. And now we can do experiments at that energy, and I've been trying to find out whether that QED test could be done at that energy. So there's some very important aspects of this. We get rid of some of the free parameters. The GU energy at Planck value is purely consequent of fundamental constants. It's just a pure number. Possibly unification with gravity, possibly with quantum aspect. Sine squared theta W is, at the electroweak scale, is result of pure numerical calculation. We don't need to assume anything. And it rises to 1 at unification. And I'm saying that the electroweak scale, the parameter is a measure of the lack of unification between the forces. True unification would require the value 1 at the beginning. There's no electroweak term at GU. There's only just the separate terms becoming equals. And again, the logarithmic term zeros in the renormalization equations at grand unification, and only the coupling constant remains. I can't find any obvious reason for this particular value of coupling constant 1 over 52.4. Maybe it can be somehow worked out for some other reason. The different fine structure constants are not independent of each other, but are related by a set of equations. So we can, if we know one, we can work out the others at any energy. And I would guess that grand unification is an asymptotic and unattainable limit on a process which either transform or break down before it can be reached. Notably, all the 3 equations are approximations, so we have to bear that in mind. Though I've done further approximation when it mattered. The gauge symmetries and hence the structure of the equations are realizable from the algebra of the charges. So I've found that out in other work, that if we got the algebra of these charges, we can work out the gauge symmetries of these interactions. They're very sensitive to slight changes outside the logarithmic term in finding MX, but once we found MX, then we get very good agreement. Now, I'll leave that out about alpha. The last point here is a bit of speculation of interest, but I don't take it too seriously, that the electroweak scale, the first point at which they can be compared, 1 over alpha 3 is 4 times alpha, 1 over alpha 2, 4 times 1 over alpha, which means the strong charge is twice the weak charge, twice the electric charge. And maybe that's in line with the algebras, as we see here, which are associated with them, because the algebras are extended, by that number in effect. So we have to have a grand unified gauge group, otherwise we can't do these calculations. Does SU5 still work? Well, I think it certainly does, either it's pure or as part of a bigger group. But if we take it as pure, we take the 5 charge units with 3 colors for the strong, and we can map these directly into the 5 Dirac operators or to the 5 quantities: mass, momentum, and energy. And they generate an overall SU5 easily enough. With 24 generators, the reason why you've got 24 rather than 25 is because you get 8 glooms rather than 9. So there we are, that's with the charges. The X's and Y's occupy the whole of the column or row in which they're in. The gluons occupy 8 of the 9 squares there. And there's one missing along the diagonal. There's one missing gluon along the diagonal because of the nature of SU3. And there's an interesting thing we can say about that, and that's using the momentum. So we do get X and Y, but they don't imply proton decay in the ordinary way they talk about. The decay they were talking about was a neutral pion plus positron. Now that's impossible because it would mean you had to eliminate the strong charge unit, and it would also disregard the dipolarity of the weak. And where I think the X and Y do manifest themselves is that in the ordinary beta decay, they're all involved. That is a strong electroweak decay. But I would say that the amplitude for the X and Y is so high that we don't normally see X and Y manifested. But they still have an amplitude for that interaction. We could imagine a 25th generator if we had gravity involved, and that would line up all the terms along the diagonal in the same way as W and Z's are lined up with gamma. So all the terms along the diagonal would be lined up in that way. But whether that can be reached or not is another issue. So I think I've said this, so I'll leave that. I'll leave that as well. There's another area which I'll only briefly mention, that the fractional charge model has very great difficulty applying the Higgs mechanism to the Yukawa interaction between the fermions. But it's very easy with this one. I can explain that on another occasion. So I'm going to conclude with this. Grand unification was one of those powerful ideas like supersymmetry, which seemed destined never to live up to its promise. And I think the problem stemmed from the lack of understanding of what reality 2 is compared to reality 1. And what we use in physics is often reality 2, whereas what we do in experiments might be reality 1. Broken symmetries, in my view, often stem from clashes between these modes of explanation. They develop from hidden symmetries, of those of reality 2, which aren't directly concerned with the observation. Those are reality 1. And I think this happened with quarks. The underlying group structure needed for grand unification operates on different rules from the QED of observation. And I'm saying we can overcome this problem if we return to a model that was proposed almost as soon as the quark theory was created, and which has never been disproved, but simply fell out of fashion. As soon as we do, we get remarkable results. Credible value for the electroweak mixing parameter, grand unification at the Planck mass, pure Coulombic forces at this energy, a connection with gravity, a meaningful connection between quarks and leptons. And we have predictions that can be tested with realizable experiments. Thank you.
Brilliant. Thank you very much, Peter. So I'm going to, do you want to stop sharing your screen?
Yes, how do I do? Yeah, stop sharing.
You can just stop sharing. There we are. So there are quite a lot of us here. So if you want to ask a question, if you move to the bottom of your screen, you have a little button there which will allow you to put your hand up somewhere. Or is it on the... Yes, you can sort of...
you mean the reactions button?
Yeah, there's a reactions button. There's something else which allows you to put your hand up. Sorry, I'm just looking for it now.
You have to click on participants.
Participants, it's in there, yeah.
Oh, it's participants. There it is. Yeah. Okay, so if you want to ask a question, can I ask people to sort of put their hands up if they want to ask a question? Lou.
Peter, could you say more about what you take to be the more detailed relationship between partons and quarks?
Peter, you're muted.
Yeah, no, it's okay. I'm no experimentalist at all, but I'm saying if you're doing partons, you're bashing a proton with some electrically charged particle of some kind and breaking, and you're trying to break out a lump, and you don't see 3 quarks at once, you see 1. So you see what comes out of that. What I'm saying is that the QED phenomenology is based on that concept. It's not based on the structure of the quarks. It's based on the structure that you actually see when you hit something with this probe. And it's like kind of breaking up a watch and saying, I've got all the parts and now can explain how it works. but you can't. And I think you've got to know how it works before you can relate them.
I understand, but it may also be the case that what people take to be partons are not quarks.
I think that's the case. They're not exactly quarks, though they're related. But they're an experimental offshoot of what comes out of a quark theory. But they are not actually quarks. They're not real particles, nor are any particles real particles. They're all quantum fields. And they're treating them as though they're a lump of something, you know, and that's what they really are. They do behave like a lump of something in some respects, but they are not a lump of something.
Thank you.
Okay. Anybody else like to ask a question?
I would have a comment, which is
Yeah, sure.
also
Dino.
a kind of question. It's about the distinction between, or better said, I think the relation between reality 1 and reality 2. And I think that this is, both exist in natural sciences theory, or and what I'm very much in favor for a theory of a point of view of reality too. For instance, just from my very scanty knowledge, but I remember an assertion by Hugh Everett about what's a model, and he says every model is correct as long as it's in accordance with the empirical evidence. So this is a kind of a connection between the point of view of reality 1 and the point of view of reality 2. And what's the kind of connection? As you said in one of your last slides for the conclusion, the outcome of all your argument is that you have to change the rules of reality 2, which were assumed right in a former stage of the grand unification. So I thank you for, because well, I cannot enter into the details, the technical details, but in general, from a purely very abstract, I might say epistemological point of view, I think that it's a real contribution, and I quite thank you for that.
Thank you, Dino.
Can I?
Peter,
Thank
do you
you,
want to
Dino.
say something?
Yeah, I'd like to say something. I think I put forward evidence that the theory has to be this because we do have experimental evidence which contradicts the other theory, because it violates its value of sine squared theta w. So it actually contradicts that theory, whereas this one doesn't. And you know, to people to say that's nothing to do with grand unification. That's more fundamental. Sine squared theta w is just electric and weak, and it contradicts that theory. The evidence contradicts the theory based on fractional charges, because we don't get the right value.
John Torday's got his hand up.
Oh, hi, Peter. Thank you for that lecture. What I found interesting was your comment on reality 2. It sounds to me like Bohm's implicate and explicate orders, that you're moving from the implicate order to the explicate order. And so my question is, when you have a grand unifying thesis or theory, does that unify the implicate and the explicate orders in Bohm's terms? And what I find interesting about that is I lay claim to the idea that our physiology is really holistically our consciousness. It's not housed in our central nervous system. It's distributed, and that what would actually is occurring is that our consciousness is the wetware of the consciousness of the cosmos. So that's rather theoretical, I know, but I'm wondering whether what you're talking about and what I'm talking about are virtually the same thing.
Yeah, I think there's probably a close relation, and you could relate it to the explicate and the implicate. Yeah, certainly. Yeah, you can put it in that terminology. Yes.
So what I've said in print is that life begins in an ambiguity. So before life occurred, it was only the implicate. It's only when life began that there was an explicate. And that process created an ambiguity because of Schrodinger's negative entropy. So what you're talking about a resolution of that ambiguity?
I think to some extent, in this particular case, I'm trying to resolve that ambiguity. But I mean, it's not much. This is a more general problem in physics. People, know that, what they call an electron isn't actually what you would think of. I mean, we think of something hitting the screen and we measure it, and that's an electron. And in a sense it is, but that's only part of it. The more fundamental story is different. And we know that. And we know that in many cases. I just find it odd that we didn't apply it in this case as well, when we had the opportunity.
And I'm of the opinion that when we are in highly stressed physiologic conditions, so Maslow talked about peak experience, that actually is a manifestation of the unification of the consciousness, our consciousness with the cosmos. So in other words, we're reconciling what you're talking about.
Oh, I can believe that. Yeah.
Thank you.
Okay. Anybody else? Anybody else like to ask a question? You can wave your hands around if you've got the camera on. I can probably see you.
Hi, Peter Master speaking. I think
Peter?
I think that one of the most convincing proofs that Peter has is in the other areas which he hasn't discussed in relation to his interiorist theory, which are, as the last speaker said, very much connected with biology. Because what never seems to get discussed in quantum physics at the sort of basic level Peter's been talking about is that really the universe evolves.
Mm.
And indeed, if the universe didn't evolve, well, we wouldn't be here. And moreover, we wouldn't be able to think that and do the thinking that's been going off at this particular in an intelligent way in terms of mathematical physics. Somehow we've evolved for all this time, and we've evolved a brain of such a structure that it's an integral part of the beginning. The only way we can talk about these things is through the thing that has evolved, which began at the beginning. That's our brain and our mind. And
Can I comment on that, Mark?
Yeah, go for it.
Yeah. So what my epiphany was the merging of phylogeny and ontogeny. So that's a wave collapse. And that actually demonstrates the energetic flow, as you were saying, Peter, from its origins, and that. So I wrote a paper many years ago talking about a biologic periodic table. So in terms of a star generating light, It starts with hydrogen and moves from hydrogen to left to right to heavier and heavier elements. The way that we understand embryology, contemporary embryology, is that it's the endogenization theory, the endosymbiosis theory, Lynn-Margulis's theory. So it's the internalization of factors in the environment on an ongoing basis in order to cope with the existential threat of, so for example, iron becomes the core of the heme protein for hemoglobin, that kind of phenomenology. So that compartmentalization of factors in the environment that pose an existential threat is our physiology. So I'm completely consistent with what you're saying. Yes.
Well, I say there's something that came up on the Forbes website about matter acting as waves. If matter didn't act as waves, do we all realize that in fact we wouldn't be here, because the sun would not just work the way that it does and give out the energy that makes life possible and makes all the matter possible that is necessary, that necessarily evolved into ourselves, or could evolve into ourselves.
Well, I think we make a systematic error. I mean, we are material. We assume that therefore everything is material, but that's reasoning after the fact. I think the actual reality of reality is energy fluxes, just as Alfred North Whitehead had suggested in his theory. So I think once you begin to understand that reality is actually energy flow instead of matter, that is a huge game changer in terms of understanding causation. The ontology and the epistemology change. And now I think quantum mechanics can be merged with our understanding of reality. So we start from the beginning instead of the end, in understanding both our own evolution and that the physical environment around us.
Peter, what do you think about this?
Matter in particle physics, quantum physics, isn't actually, we don't really think of it as matter. It's really interacting fields, which may be a similar concept. It's really just interacting fields, and an electron is a manifestation of the electron field, and so forth. And so it's convenient for us to think of them as particles and to talk about them as particles, but like matter, but they aren't really matter in that ordinary sense. And we've gone beyond that in the physics. We don't really think that at this level. It depends what level you're speaking, whether you think of it as matter or not.
Mike,
well, I mean, they wouldn't be
quantum mechanics was that it doesn't align with what we experience.
They wouldn't be an electron if there wasn't a universe. The universe is one thing. We don't know what it is, but we do know that it's, or we think we know that it's totally connected. Everything in it can't just exist on its own. So an electron, when we talk of an electron, we have necessarily to think of it in the context of the universe. And it doesn't matter whether the universe is a multiverse or just the thing that we see, which is the connection of the galaxies and black holes and the dark matter. But basically, at some level, it is just one thing, and everything else is just a part of it. And I think that is where we should really start to create our models. That and this idea was given to me by Clive Killmister, one of the members. He noted that in John Conway's work, for example, that really the whole number system could be thought of as a set of automorphisms, and that there was, as Conway proved, just a unique birth order automorphism, which we could think of as the universe of as the universe evolving through a series of automorphisms. And if we approach things that way, anything that appears at some stage in that evolution will be part of the universe itself.
Mike Manthe has been very patient. Mike.
I think Mike Manthe would probably agree with that view.
Yes, Peter, I'm just wondering, in my paper in 2 weeks on Monday, I'm presenting a structure that has U1 cross SU2 cross SU3 cross SO4. In other words, it's got the standard model and space-time. My question is, what I've done is purely combinatorial. There's no physics in it, none. It's purely combinatorial, and in the Clifford algebra over Z3 equals 0, 1 minus 1. My question is, since I'm doing this purely combinatorial and getting the same kind of a model, how does this impact your reasoning?
Well,
is that Peter or this Peter?
Yes, yes,
hello? Peter? Peter Rowlands?
Hey, right. Okay. Sorry.
Peter Rowlands.
Yeah. I'd have to see what you're going to say. I don't know what you're going to say, how it would
Peter
impact.
Rowlands.
Yeah, I'm sorry. Yeah, I'd have to see what you're going to say with this model, how it would impact. I don't know. I mean, I'm saying that if you're talking about grand unification and you're talking about grand unification,
purely combinatorial.
Yeah, I'm saying if you're talking about grand unification, well, sure. If you're talking, I mean, in many ways, my work is purely combinatorial because it can be all reduced to algebra. But I haven't done most of that today. I've done something else. But I'd have to see what you're going to say about the SO4 part. You know, I can't really comment until I've seen that.
But I mean, the advantage of the model that I'm talking about is that, in fact,
okay, fair enough.
It's even
leave it there.
Evolution evolves an infinite number of new states of matter, and each of these new states of matter has a unique new process. So we are actually creating new whole hierarchies of self-organization, and we would be one of the hierarchies, and so would our brain, and so that would connect in having what Peter has just described. Since the whole idea is based on the work I've done with him and his wonderful idea of the this group's wonderful idea of the combinatorial hierarchy, and then after that Peter's idea of the rewrites system.
Yeah. Thank you, Peter. I mean, John Torday is talking next week, very much along these lines, I think, John, aren't you?
Yeah, I thought maybe another way to, with all due respect, that I would restate what I was trying to say is Darwinian evolution is purely material. It's based upon a number of offspring. So it's just a bean counting kind of thing. It's a counting. And the other prevailing, and so Darwin was a gradualist. Gould and Eldridge's paper in '72 was about punctuated equilibrium. And I think about those things in the same sense as Niels Bohr's explanation for light as being particle and wave. It's how you measure it. But what I spent 50 years doing in the laboratory was cell-cell communication through soluble growth factors. So it's a communicative process. And if you look, and in that sense, It's quantum. It's a quantum mechanical process. Well, I agree with you, Peter, but I don't put much weight on the brain. It's a distributive process because even a unicellular organism is conscious, in my opinion. And Reber and František Paluška wrote a book about that, about the single cell being conscious. Consciousness is just the, the division of the internal interstices of biologic systems separated as a barrier, as a boundary from the physical world. So consciousness really is universal, in my opinion, biologically, and perhaps even beyond that.
Okay.
So I look forward very much to hearing your talk, John, next week, and then perhaps we can exchange some ideas. I mean, Peter and I have several papers on, and I have some other papers with a German mathematician called Walter Schwemp, and we're talking about organisms and life as being sentient.
Mm.
So that
Okay.
it has what connects the inside of us to the outside, and how we can perceive in terms of what goes on inside us, what is going on outside of us.
Yeah.
But we don't really want to get into this now.
Okay, no, I was going to say we've got weeks to explore this. John Hyatt had his hand up, although you might have put it down now. But John, did you want to say something?
Well, it was related to what people were talking about a while ago now, but just with Whitehead and Science of the Modern World, he seemed to, I mean, I'm an artist, so correct me if I'm wrong, but he seemed to be saying that there's a reality 3, if you like, which on top of Peter's reality 1 and 2, and that everything is just event, and that if everything is just event, it's not really energy that's the driving force, it's entropy, because entropy is the only thing that changes.
Mm. Peter?
Yeah, well, I think that's true.
In the model that I'm working on, entropy comes into it. The first, you don't just need the first law and a conservation of energy, but you need the second law. And one of the wonderful things that Peter discovered was that, in fact, the second law can work inside the first law.
Okay, can I just say that, but from what John said, I think that's almost certainly true, because I don't believe that energy moves. Fundamentally, I think energy is just there, and I don't believe it is swapped or changed or anything like that. It changes its structure, and that is what entropy is all about.
Yeah, that's what I mean.
That's what we're really talking about. It's not an energy flow. It probably isn't. It is certainly is an entropy flow, because that's what determines change. Yeah.
Yeah.
But okay.
Okay. Anybody else?
Can I just comment on that? So basically, I mean, biologic systems are all about calcium flows ultimately. And that's electron flow. So in my mind, as a biologist, that is energy, Peter. So I think I understand what you're saying, but on the other hand, I mean, if I put 2 electrodes in a potato, I get electron flow. I get a light bulb turning on. So that's energy, no? Am I missing something?
Can I just ask if anybody's got questions on particle physics or grand unification or anything like that? Or what I talked about.
Can I ask you a question, Peter? Because last year, Mike Holden gave a wonderful presentation about your work. And really, it was focusing around the potential for doing experiments to prove your nilpotent quantum mechanics approach.
Yes.
And today, you are very definitely pointing at a whole bunch of other experiments which also could do the same thing. How do we organize ourselves to do this and get some of this stuff done?
Well, I'm talking to colleagues in the department who were working at CERN, particularly Andy Mehta, and he says that it's hard to do a QED test with the existing arrangement, but I don't think it's impossible. So I keep pushing to see if they can do it. But he says they can do a QCD test, the strong interaction, and there might be a slight difference from the routine values to the values I would give. And he's sent me data on that I can look at.
Yeah. So, I mean, but this is important, isn't it? Because this is not just about this particular issue of that you've addressed today, but it's about your whole approach. This could be a very powerful foundation for actually saying, look, folks, this is the way to look at it.
Absolutely. We missed out on a whole load of stuff because of being determined to stick to the reality one approach. We missed out a whole load of we could have made. I mean, I haven't included it all in here, but it makes sense of a lot of things like CP violation and so on. You can make sense of them using this approach. Now, I haven't had time to talk about them, but there are definitely a lot of problems with the way things are done at the moment. People sort of throw their hands up in the air and say, we can't do anything. We can't get any good results. It won't work. We can't get any further than we've got. But they're wrong, because they've had something there available for for more than 50 years, which they could have used. And it wasn't produced, it wasn't a backwoods production. It's a major paper, often cited. But only part of it is cited. And Namba was a particularly important person in the field of particle physics. And so he died a few years ago, and all the obituaries mentioned this work. But not one of them said, let's have a look at it again.
Okay. Anybody else? Particularly anybody who has the wherewithal to get someone organized to do some experiments to prove this stuff, or something completely different.
Peter, can I ask a question? You focus very heavily on the absolute coefficients in your equations. I was just reading Henry Bortoff's book, in which he contrasts Newton versus Goethe. So specific measurements, refractive index versus a more holistic way of thinking, which suggests to me that the absolute number is maybe not absolute. So, is the tail wagging the dog with regard to the coefficients you're addressing?
I don't think you can do particle physics without numbers. I just don't think you can do it in a holistic way like that. I mean, you may get some insights, but you can't actually do it. And but whatever Henry Bortoff said, most books who talk about the Newton-Goethe dispute, well, not that Newton did dispute with Goethe because he was already dead before Goethe was born, but the experiments that Goethe put forward to try to refute Newton had already been done by Newton, several of them about light in the shadow, and he showed how light, and shadow interact, and they don't support, what Goethe said. But if he wanted to say something different, more holistically, not so scientific, then that's fine. I have no objection to that. But if you want to understand what the nature of fundamental forces are and so on in nature, you've got to do mathematics. You've got to do it this way. Anything else won't work at all. And you've got to be strict about it, because if you aren't, if you're fuzzy about it at all, you won't get anywhere at all. On this particular topic. On other topics, maybe it's different. But this one.
Okay. Maybe we should stop in a second, but just if there's anyone else who's got a burning question, either wave your arms around or stick your hand up.
May I?
Yes, Dino.
If I understood correctly, you mentioned a holistic approach, and I just wanted to say that a holistic approach involves self-reference, and that's what John said before. Is consciousness to me. It's just self-reference from a formal point of view. And then you can deal with it with formal means taking into serious account of what it means, comparing reality 1 to reality 2, to admit an ambiguity between a quantitative and an operational understanding of numbers in Clifford algebras, as I mentioned yesterday, and so on. So, because the logic of self-reference is not the conventional logic we are taught at undergraduate classes. Sorry, that's what I wanted to say.
Okay. Peter, do you want to respond to that? And Tom Hyatt's also got a question.
I don't know.
Well, I mean,
Excuse me. I don't. It means me. I don't know how I can respond to that because it seems perfectly sensible to me.
Okay.
I don't really wish to say anything against it.
All right, Tom.
Hiya. Thanks, Peter. That was really interesting. I didn't understand all of it, but I got quite far before it started slipping away. I was just wondering whether there was, with a view to, I guess, the Mark's point about where it goes from here going forward. Are there any kind of problems with it, with your ideas that you're trying to iron out? Like, what's the day-to-day, or are you just waiting for someone to do the experiments to try and determine either which way?
Well, I don't know any particular problem with it because it was remarkable that one set of calculations and another set of calculations converged, and if that happens, usually that's a good sign. What I am just really waiting for people to realize that they can't carry on as they're doing and they've got to try something else. But certainly experiments could decide it if we could do good enough experiments. And I do know people at CERN. We have colleagues in the department who work there and work on these experiments. We've got colleagues who work in the Atlas experiment, and there is a possibility of something being done, or of me getting data from them at least to verify what I'm talking about. And that's not impossible. As I say, I've got a colleague who's particularly interested in this, who works on the Atlas experiment. And I would have been talking to him now if it hadn't been for the lockdown. Andy Meta, I mentioned his name, yes.
But that's what you want, Peter. We wanted to get someone in the group who's an experimental, a team of experimental physicists, and if you could get your people, hooked on that, and actually try and devise a particular experiment with them, guiding you as to what the kind of thing is necessary.
Well, I think
you've got all the background, but you need someone who has, knows how to put the nuts and bolts together, so to speak.
I think with Atlas, that you don't actually need to so much devise an experiment as look at the data and devise a way of looking at the data. And then I think it's more of that, and that's what I'm trying to get people to take an interest in. But I think there is already experimental evidence in the favor of this, because the sine squared theta w is wrong in the theory they're using and right in this theory. So it's already pointing in the right direction. So I don't know how many experiments you've got to do to convince people. I have said for a very long time about this value of the three fine structure constants. We've got exact ways of determining how they will behave over a long energy range, and that's open to experiments, and we can look into that. It's available.
Just quickly, John.
Yeah, can I just synthesize what Dino was saying with what Peter was saying, Peter Master was saying, to address Peter Rowland's? So Daniel Fels has shown that photons can affect cells directly. Cells are made of lipids. Those lipids have a refractive index. So what I'm saying to you, Peter, is do we need to have a correction factor for the interface between the biology and the physics in order to understand the precise numerical values that are being used in your elegant mathematics? Do you know what I'm saying?
Well, for the problem I'm dealing with, we don't really, because it doesn't depend on the human perception in that way. But you know, if you're talking about other types of things, for example, cells and photons affecting cells, yeah, we need a lot more information than we've got. And we are beginning to connect quantum mechanics with biology, and there's been quite a few things going on that. I'm actually, you know, working on one thing, which I don't want to talk about at the moment, but I'm working on one thing, one particular issue on that. And, we're already doing that, and we've got to develop, you know, quite exact theories to make sense of them. I don't know about an interface. I think the physics is still physics, whether it goes on in biology or not, and the biology is still biology.
But the salient feature I'm talking about is what Dino said, which I fully agree with, and that is that what I'm talking about is consciousness. So in order for any of this to make any sense, we have to be conscious of it.
Oh, yeah, we have to be conscious. Yeah, as Peter said, Peter Master said, we've written papers on this issue, starting from the rewrite structure and so on. But we understand that this is part of the process, and we don't think it isn't. But if I'm talking about something where I know if we weren't conscious, we wouldn't get anywhere at all. But assuming that we're conscious, we carry on doing physics as physics, and with quite a lot of success.
Well, in my experience, more than an hour and a half in Zoom does something to your consciousness, which isn't necessarily too good. So I do suggest we park this for today and come back tomorrow when Lou is going to be talking about, I can't remember what, Lou, just tell us quickly what you're going to be talking about tomorrow.
The title of the talk is Space-Time Algebra, but it will be whatever I am talking about at that time.
Great. Well, I look forward to it, and thank you so much, Peter, for a presentation which I'm going to watch a couple of times, and I'm sure each time I watch it, I'll understand something more. But I think that the issue about experimentation, to me, seems incredibly important and potentially exciting. So thank you very much.
Thank you.
And we'll see you all tomorrow.
Yeah.
Andrew, you want to say something?
Thank you.
Are we waving? Okay. All right. Bye-bye.
Bye.
Bye-bye.